Hi everyone, today we're going to take a look at a Keithley current source, in particular this Keithley model 225, which was manufactured way back in 1976. This particular unit can provide you with a current source from 0.1 nanoamp all the way up to 100 milliamps in 7 ranges, and with each of those ranges you can select the individual current by the use of 3 decade switches. The unit has an accuracy of plus or minus 0.5% or better, and a load regulation of plus or minus 0.005%. The unit is quite heavy. It weighs around about 8 pounds, or in kilos about just over 3.5 kilos. And today you can find these second hand, but they're still quite pricey, and they still fetch around £200 to £300 a unit. So what we're going to do today is have a look at this unit, take it apart, and then just see what makes it tick. So let's have a look. So let's have a look at the front controls on this current source unit here. The output from the unit is taken from this BNC socket there. On the lowest current range, which is the nanoamp range, it has an output impedance of 2 teraohms. The top controls here are the selector switches for the current. This one on the right hand side here is the range switch, which is selecting the current range from nanoamps to milliamps in 7 ranges there. And these are the 3 decade settings for the individual current on each range. On the end of this particular range selector you have a variable adjustment control there, which is a fine tune or a trim control, and that can go from 0 to 10, and effectively if you increase it to maximum, that's clockwise, to 10, it has the equivalent effect of adding 1 digit onto this least significant selector switch here. Under normal conditions, using it if it's fully calibrated, this unit, you would have this particular trim control turned fully counterclockwise. The on-off switch for the unit is here, so switching that on. What you will notice now is that one of the lights will come on near the selector switches here, and this would normally indicate a decimal point. You have a light indicator there, you'd have another one here, and you'd have another one there. At the moment, because the light is there, it would mean that these 2 digits are the significant digits, and then this one is the decimal place digit there. If I change the range switch here, as I step the range down, you see that the decimal point has now moved here, so that's the significant digit there, and these are the 2 decimal places. If I then move it on to the microamp range, this is the highest microamp range, you see the decimal point has moved there, which means that all of these 3 are the significant digits. If I go down the microamp range, you've got the 2 significant digits there and the decimal point there. So you get the idea. As we switch down the ranges, the decimal point will move. The controls here at the bottom, this particular one is the standby, which is the output selector switch really, which can go from standby to a positive output or a negative output on the output socket here. So at the moment it's in a standby position, and you can switch to positive out, into standby again, and then you can turn it to negative out, back to standby. This control here is the voltage compliance control, and that can provide anything from 10 to 100 volts on the output. It's set just by variable adjustment. If you have a resistive load connected to the output there, and the value of the resistance and the current source which has been set, if the calculation of that suggest that the voltage is greater than the compliance voltage, the limit light here will then come on and it will go into a constant voltage mode. If you use this unit with an inductive load on the output there, you need to switch in a filter which puts a 0.1 microfarad capacitor across the input terminal. For normal use, you would leave the filter switch in the off position. The second output connection here at the front, which has a cap on it, if I just remove that cap, you have another BNC connector there. That is not normally used unless you wanted to use the unit in a floating output operation where you wanted the output to be above a ground level, so you could have it floating up to plus or minus 500 volts. So those are then isolated from the earth. Under normal circumstances, this output terminal is covered and we just use the output there. And in that case, on the rear of the unit, as I'll show you shortly, there is a link that connects the low output to the ground output, and it's that link that you would remove if you wanted to use this in a floating operation. If you did decide to use it in a floating operation, you'd need two cables coming out of this unit. Under normal conditions, we just need one coaxial cable coming out. Right, if we look at the connections on the rear of the units, there you can see we have the ground terminal and there we have the low output terminal. I mentioned a moment ago that under normal operation we have a link joining those two together. If you wanted to use the unit in a floating mode operation, you would remove that link. On the rear you also have covered at the moment the output socket, so you can supply output from the rear of the unit as opposed to the front. And you also have another BNC socket there where you can connect in, you can feed into it a modulation signal to modulate the output current. Under normal conditions, both of these two BNC sockets are in fact blocked off. In order to demonstrate this to you, I've just got my Keithley picoammeter here, which can check from 1 milliamp down to 1 nanoamp range there, and I'm connecting it onto the current source unit here at the output socket using a screened BNC cable. I currently have the current source unit. The selector range switch here is set to the lower of the 2 milliamp ranges, which means that the decimal point is there. I have my picoammeter set for the 1 milliamp range. If I switch the first significant digit here up to 1, we should read 1 milliamp exactly coming out. So we've got 1.00 of a milliamp, and you can see there quite clearly on the picoammeter there we have 1.00 milliamp. If I adjust the second range switch there, we can go to 1.1. If I do the third switch, we go to 1.11. So I can set these switches. There I'm on 1.31. The ammeter is showing 1.309, which is nearest to 1.31. If I go to 2, I've gone over range on the meter, so we have the flashing there. So I'll just go back to the 1. So we see the current source at the moment is set to 1.41 of a milliamp, and the meter is showing 1.41 of a milliamp. That should now read 1.42. If I increase the first decimal, let's go to 5, that should be 1.52, 1.62, it should be, it's reading 1.619. I'll now switch the unit to one of the microamp ranges. I'll go to the middle of there's 3 microamp ranges here, so I'll go to the middle one there. You can see the decimal point is there, so these will read the 2 significant digits here and the decimal place there. So at the moment it's set to 16.2, that means it's 16.2 microamps. If I select the range on the meter, you can see there we're reading 16.1, 16.2. The current source unit is now set to 26.2 microamps. Increase it to 3, so it should now be reading 36.2 microamps. It's reading 36.2 or 1 on the meter there. Let's move it up to say 6. I've now set this to 66.2. Let's alter this to 66.6, and we're reading at the moment 66.5 on the ammeter. So if we now switch to the lowest current range, which is nanoamps, the decimal indicator light is now there, so these are the significant digits and there's the decimal place digit. At the moment it's set to 66.6 nanoamps, so I need to switch the meter to the 100 nanoamp range. Now when you get to the low ranges, then the cable that you have connected to the meter plays a significant part in what's displayed. If you're picking up any hum or anything on this cable, you can see as I move the cable around, we affect the reading on the picoammeter. I'll just move the range switches down here to, that should now be reading 16.6 nanoamps, and on the meter we're reading at the moment 16.9. So there's a slight discrepancy there, which is probably to do with the lead I have here at the moment. It's not ideal, it's not a very good quality lead. And one thing I should point out is, for safety reasons, if you have the dials here set all to 0 and you have nothing connected on the input there, no resistive load on the input, you can get up to 100 volts coming out of there. So for safety reasons you need to be careful. They do suggest in the instruction manual that when you're selecting ranges or you're at the 0 setting, to leave the unit in a standby position, which means that the output is then isolated. The correct procedure is you set your current source requirement here with the range selector and the switches here, and then you switch the standby position, the output selector, to either plus or to minus to get the output there. Okay, so let's now take the cover off and have a look inside the unit. Right, I've removed the 4 fixing screws, 2 at either side of the case, so I can now just lift the whole case up. And we can see inside the unit. Well, here you can see the power supply section of the board. There's the mains transformer, and you can just see down around the main transformer you have 3 bridge rectifiers. This particular unit is actually, we'll get both negative and positive voltages coming out from the power supply. We have a minus 130 and a plus 130 volt supply, and then we have a plus and minus 10 volt and a plus and minus 12 volts from the power supply here. These are the main smoothing capacitors on the power supply, old-fashioned paper electrolytic type. Looking towards the back of the unit, behind the smoothing capacitors there, you can see we have two power transistors plugged in, and they are the series regulator transistors, the complementary pair, feeding the output current to the output source on the meter itself. Just have a close look at this part of the circuit here, just in front of the transformer. We actually have two ICs there. This particular one with the heatsink around it is a voltage regulator IC. It's the Motorola MC1723CG, and that's used in the 12 volt regulator circuitry around here. And this op amp here is again a Motorola type. It's the MC1439G. Again, that is also acting like in a buffer in the 12 volt voltage regulator circuit here. And this preset there sets the 12 volt DC in this regulator. You have two other small power transistors here, and they're used in the plus and minus 10 volt regulator circuit together with these two Zener diodes there. Just a closer look here at towards the front of the board. We have two small little power transistors there with their heat sinks on. They're used for generating the compliance voltage, the positive and negative compliance voltages of 100 volts. These two particular transistors here are controlled by there's two Zener diodes, one there and one there, and these two presets here set the positive and the negative of the compliance voltage. Down in the bottom corner there you'll see a small transformer. That's the modulation transformer, where we have an output on the back where you can modulate the current source. All of the other components on the main board here, all discrete components, all transistors and just conventional resistors and capacitors and diodes. There's nothing really special there at all. Here you can see the main current selector switch for the 7 ranges, and around these two wafers here we have the selection resistors. There's 7 resistors there, all high precision resistors going around the wafers, and they are 10 ohms, 100 ohms, 1k, 10k, 100k and 10 meg. So those are the range selection resistors there for the different ranges, the different current ranges. Here is a closer view of the range selector switch, and at the end of it you can see the trim control there. Here's another view of the range selector switch, and there clearly you can see some of the resistors, and here's the trim pot and the switch at the back. You'll find there's a couple of transistors down there which are linked together thermally for temperature compensation purposes. Here you can see a closer view of the components below the current range selector switch, and I'll just point out there we have 2 transistors thermally linked for temperature compensation there. Here we have an additional printed circuit board where we have the selection switches here for the particular current. These are the 3 decade switches, and the high precision resistors are all mounted on this printed circuit board here. I'll see if I can get a better view of that with the camera shortly. Now this particular unit forms a Kelvin Valley divider network for precisely switching the current range through the different settings for a particular current source. And here you can see the neon indicators there, the lights for the use for the decimal place indications on the front control. Well, there you can see a slightly better view of the selector switches there and the precision resistors running across the board. Here's another view of the printed circuit board here, the back of the printed circuit board, where we have the 3 decade switches with all the precision resistors on. Just below it you may be able to see there we have the output selector switch, and then there just at the back there's the large potentiometer, which is the voltage compliance potentiometer, giving us 10 volts to 100 volts. Well, I hope you found that teardown of this Keithley 225 current source unit of interest, and I'll see you all again next time. Bye for now.